Right now, inside the very thing you're watching this on, there is a tiny worker doing one small job over and over, 1 billion times a second. And it has kept your entire day running without you ever once saying thank you. It can't paint, it can't dream. It's honestly a little bit dumb. Give it a job, and it does exactly what you said, no more, no less, faster than you can finish this sentence. It answered your alarm this morning. It's holding this video together right now. And by the time we're done, you'll understand not just this little worker, but the strange, roaring machines that are teaching computers to think. Let's meet it. Picture a kitchen, not a fancy one, just a counter, a stove, and one cook standing very still, waiting. This cook is your CPU. The letters stand for Central Processing Unit, but forget that. It's the chef. It's the one who actually does things inside your computer. Every tap, every scroll, every song passes across this one little counter. Here's the first surprising thing about our chef. It is not a genius. Watch what happens when an order slides in. The chef reads the ticket. We call that fetch. It figures out what the ticket means, decode, then it does the thing, execute, and instantly it reaches for the next ticket. Fetch, decode, execute, again. That's the whole ritual. Read, understand, do next forever. And the tickets are almost silly. Add 2 and 2. Is this number bigger than that one? Move this value one shelf to the left. No ticket ever says make dinner. Every big thing your computer does is really a pile of these tiny baby tickets, done in exactly the right order. So how does a chef this simple run your whole life? One word, speed. Our chef doesn't finish one ticket a second, not 1,000. It finishes billions. When you hear this chip is 3 gigahertz, that's the number. 3 billion beats every single second. The chef is dumb, but it is stupidly, gloriously fast. Let's watch a real morning. Your alarm goes off. In that instant, an invisible checklist begins and your chef starts cooking tickets. Light up the screen, load the time, fade the wallpaper in, listen for your thumb. You open a song. More tickets. Read the file, unpack the sound, push it to the speaker, 60 times a second. You text a friend, tickets. You check the weather, tickets. All day long, one chef at one counter, doing one thing at a time so fast that your whole life feels smooth and instant. And it's wonderfully, ruthlessly literal. It never guesses what you meant. Which is why, when just one ticket is wrong, the whole dinner comes out wrong, instantly, with total confidence. That's a bug. One bad ticket in a pile of 1 billion. Now the chefs got better every year. Faster hands, and engineers found a clever trick. Instead of one chef, put in a few, 2 chefs. 4. Today's laptops have maybe 4 to 8, the biggest desktop monsters, 64. We call each chef a core. For decades, this was the whole game. Faster hands, a few more chefs. And it worked beautifully until the orders changed shape. Here's where our story turns. For most of computing history, the plan was simple: make the chef's hands move faster. Speed up the beat. 3 gigahertz, 4, 5, every year a faster chef. But you can't speed up hands forever. Push a chip's beat higher and higher, and it does something very physical. It gets hot. Cram those beats too close together, and the chef's hands, basically, catch fire. So somewhere around 4 or 5 gigahertz, we hit a ceiling. A real, stubborn wall made of heat. The single chef could not get meaningfully faster. Physics said no. That would have been fine, except the orders were changing. Some jobs aren't one hard thing after another. Some jobs are the same tiny thing done a staggering number of times. Take one frame of video on your screen. A single 4K image is 8.3 million pixels, and every one of them needs almost identical little color math done to it. Now do that 60 times a second. Or think about the math behind modern AI, multiplying giant grids of numbers. The same simple multiply and add, repeated billions of times. Hand 8 million identical chores to one chef, even a god-tier chef with blazing hands, and what happens? A line. A line out the door, around the block, into next week. The chef flips one burger at a time, perfectly forever, and the orders just pile up. This is the wall, not that the chef is slow. The chef is astonishing. The wall is that one chef, doing things in order, is simply the wrong shape for a job that's a million copies of the same thing. So the engineers asked a different question. Not, how do we make the chef faster? Instead, what if we stopped hiring geniuses and hired a crowd? So they built the opposite chip. Meet the GPU. If the CPU is one master chef, the GPU is a stadium of line cooks. Thousands of them. And I need you to meet one because he's important. This is Pip. Say hi to Pip. Pip is not smart. Pip knows how to do one thing, the small stuff. Add these two numbers. Color this one pixel. That's it. You could not send Pip to run a kitchen. He'd panic. A GPU was born for exactly one purpose: drawing graphics. Millions of pixels, 60 times a second. That fire hose of identical little chores that broke our poor master chef. So instead of a few huge clever cores, the GPU packs thousands of small simple ones. Thousands of pips. Let me give you the honest numbers. A top gaming chip, the RTX 4090, has 16,384 of these little cores. The newest ones cross 20,000. Meanwhile, our mighty CPU has 4, 8, maybe 64 at the extreme. But wait, you say, isn't each pip 100 times dumber than the master chef? Yes, absolutely. One-on-one on any single job, the master chef destroys Pip. 10, 20 times faster. Pip loses every duel, but there aren't two of them. There are 16,000. And here's the line to remember. We'll come back to it at the very end. Pip was never supposed to be smart. He was supposed to be 10,000. So how does a crowd of pips actually work? You don't give each cook their own recipe. That would be chaos. Instead, you give all of them the same instruction. One shout across the whole stadium, and each cook does it on their own little scrap of data. Flip, and 10,000 hands flip 10,000 patties in the same instant. One shout, 10,000 results. Engineers call this the stadium wave. The GPU bundles its cooks into little squads, 32 at a time, and every cook in that squad does the exact same step on the same beat, each on their own pixel. Same instruction, many hands. That's the entire trick of the GPU. And it maps perfectly onto the jobs that broke the chef. Coloring 8 million pixels isn't 8 million different problems. It's the same little color math, millions of times. Picture 10,000 kids with one giant paint-by-numbers poster. The chef colors it square by square. The kids color the whole thing in one breath. So put the two side by side. On one hard, twisty job, the master chef wins easily. But on 8 million identical burgers by lunch, the chef is still on burger number 1, while the stadium is already wiping down the counters. That's why a GPU can train an AI model up to 250 times faster than a CPU. Not because any single pip is fast, because there are so many of them, all flipping on the same beat. Many hands make light work. Now, before you fire the master chef and hire a million pips, let me be honest. The GPU is amazing, but it is not magic, and it fails in very specific ways. Remember, the whole crowd only works when everyone does the same step. So what happens when a ticket says, if your number is big, do this, otherwise do that? Now half the cooks need to go left and half need to go right, but they can only move as one crowd. So the GPU makes the whole squad do both paths, one after the other, with half the cooks just standing there, idle. A branchy, decision-heavy job turns the roaring stadium into a very expensive nap. That's the master chef's home turf. Second, some jobs simply can't be split up. If step 2 needs the answer from step 1 and step 3 needs step 2, you can't shout it to a crowd. Someone has to do it in order. For that kind of job, a lone pip is actually slower than the chef. So it's not GPU good, CPU bad. It's shapes. One hard thing in a chain, the master chef. The same easy thing a million times over, the stadium, which raises the real question. When a job comes in, who gets it? Meet the last character in our kitchen, the head waiter. In real terms, this is your operating system and its scheduler. Windows, Mac OS, whatever's running the show. Its whole job is to take every order and decide, chef or stadium. Now here's the thing people get wrong. The waiter doesn't sniff each job and guess. It's decided ahead of time by the people who wrote the program. When a normal app does normal work, checking email, running a spreadsheet, that code was written for the chef, and it runs on the CPU. A program only goes to the GPU when it specifically asks. When a game or an AI tool says, in effect, I have a mountain of identical math here, it uses a special handoff. A language like DirectX for games or CUDA for AI. And that's the moment the work gets carried to the stadium. And your laptop has one more clever trick, because it cares about your battery. Fancy laptops don't have one GPU, they have two. A tiny, power-sipping one baked into the CPU, and a big, hungry, powerful one with its own memory. Most of the time, you browsing, you reading, you watching this, the big stadium is asleep. Dark, silent. The tiny cook handles your desktop, and your battery stretches for hours. But open something demanding, a game, a video editor, an AI model, and the waiter flips the lights on, and the big stadium roars to life. The fans spin up, the laptop warms in your lap, the battery starts falling. That's not a malfunction. That's 10,000 pips clocking in. Let's follow one job all the way through. You opening a game, you double-click. The chef wakes up and starts running the game's brains, the rules, the score, where the enemies are, what your buttons did. That's twisty, decision-heavy logic. Perfect chef work. But now the game needs to draw a frame. Millions of pixels, right now, and again in 1/60th of a second. So the game calls out through DirectX, I need the stadium. The head waiter wakes the big GPU. And now the two work together in a rhythm 60 times every second. The chef figures out what the scene should look like and hands over a stack of drawing commands. The stadium takes them and paints, thousands of pips coloring the frame all at once. The finished picture goes up on your screen. Then, chef thinks, stadium paints, screen updates. Again. And the second you quit, the stadium goes dark. The fans settle. The battery calms down. The big cooks clock out, and the tiny cook takes the counter back. 2 chips, 1 head waiter, trading 1,000 jobs a second so smoothly you never see the handoff. Now, one more question. What if the job is so big that a whole stadium of pips still isn't enough? To train the biggest AI, one stadium is nowhere near enough, so we do the wild thing. We start stacking stadiums. Start with one metal box holding 8 GPUs, wired tightly together. That's one server. Now the AI is too big even for that, so you chain the buildings into a rack. NVIDIA newest rack fuses 72 GPUs into a single machine that behaves like one giant supercook. But to act as one mind, all those cooks have to share notes instantly. So the GPUs are wired together with a private superhighway called NVLink, moving nearly 2 terabytes every second between chips. Picture pneumatic tubes running between every floor of every building. Then you link thousands of those racks into a cluster, and now you don't have a building, you have a city. One real example. A cluster called Colossus went from 100,000 GPUs to over 200,000, and it's still growing. And here's my favorite turn in the whole story. In this monster city of stadiums, where did the master chef go? He's still there, but his job shrank. In a giant AI machine, the CPU isn't the star anymore. It's the dispatcher. It loads the data, hands out the work, and collects the results. The genius became the manager. This costs a staggering amount of power. One of these racks can pull 120 kilowatts, as much as 100 homes, and runs so hot it has to be cooled with flowing liquid. A whole cluster can draw 250 million watts. So who on earth can afford a city of stadiums? Almost nobody. One of these top AI chips can cost as much as a car. A full rack, more than a house, and you need thousands, so the world figured out something sensible. You don't build the city, you rent a corner of it. This is the cloud. Giant companies build these roaring warehouses of GPUs, and then they rent them out by the hour. Need a top-tier AI chip for an afternoon? A few dollars an hour. Need 1,000 of them overnight? You can have them and hand them right back at dawn. And that's the quiet revolution hiding behind the AI boom. A curious kid, a two-person startup, a scientist with a big question. None of them need to own a warehouse. They just borrow a stadium for an evening. The most powerful thinking machines ever built are, for a few dollars an hour, available to almost anyone. Let's put it all together, one gentle pass. At the heart of your computer is the CPU, the master chef. One worker, brilliant and blazing fast, doing tiny tickets one at a time, 1 billion times a second. It runs your whole day, and it's a little bit dumb, and that's fine. But it hit a wall. You can't speed up one chef forever. Push the heat too far, and the kitchen melts. And meanwhile, the jobs got huge and repetitive. Millions of pixels, billions of identical sums. So we built the opposite, the GPU. Not one genius, a stadium of simple cooks, thousands of pips, all doing the same step on the same beat. Useless for twisty thinking. Unstoppable for the same small job 1 million times over. Your head waiter, the operating system, sends each job to whoever fits. Chef for the thinking, stadium for the painting. And when the job outgrows a single stadium, we stack them into servers, racks, and whole cities of GPUs, with the chef stepping back to direct traffic. And here's the humble truth under all of it. None of these chips is actually smart. They add, they compare, they move numbers one shelf to the left. Every wondrous thing your computer does is that, done fast enough and many enough to look like magic. It isn't magic. It's just millions of tiny, honest tickets done in the right order. So here's where we land. The thing in your hand right now holds a version of this entire story. A little chef quietly running your day. A stadium of cooks asleep until you need them. A head waiter trading 1,000 jobs a second so smoothly you never notice. And somewhere in that stadium, still flipping, still dim, still perfect at his one small job is Pip. Remember, he was never supposed to be smart. He was supposed to be 10,000. So the next time your phone wakes up before you do, or a game paints a whole world in a blink, maybe say it just once. The thing they've been waiting for all day, 1 billion beats a second and never once heard. Thank you.